Ryan, do you have a preferred position for where your little box with your video is?
Um, Not really. I mean, probably upper right-hand corner. I don't know. It probably varies from slide to slide. If it does happen that it's a problem on a particular slide, just shout at me and I'll
Yeah,
pause
I'll
and
move it
remove
around.
it. Okay.
Okay, so thank you, Ryan, for joining us. I know it's a busy time for you. Ryan is officially starting at UC Santa Cruz, coming from the Mag Lab. And he's also been a participant in FQM schools over the years. Um, and so, can everyone hear Ryan in the back? Good.
Oh, yeah.
Yes? Okay, so let's begin. Thanks, Ryan, for joining us, and please go ahead.
Okay, thanks, JP. By the way, if I do start to trail off or you can't hear me, just shout at me and I'll try to change what I'm doing. So I guess I'll start with an announcement and an advertisement. I am really extremely freshly relocated to the Department of Physics at the University of California at Santa Cruz. The lab that I'll be setting up will be one that's focused on materials synthesis, as well as measurements across a wide range of conditions, studying quantum materials. For folks that are in the audience, if this is the sort of thing that you're interested in, and you're looking for a postdoc position in about a year, there will be a job advertisement. Or if you know undergraduates who are looking for a group like this, please spread the word. I'm interested to take some graduate students now. And by the way, it doesn't hurt that we're only 5 minutes from Natural Bridges Beach. So that's pretty fantastic. Okay, so the title of this talk is Crystal Synthesis, Enabling Studies of Quantum Materials. What I'm going to do in this talk is to make some sort of broad perspective statements, and then get into some of the details of how various types of crystal growth actually work. And a lot of these are going to connect directly to the practicals that you all will be doing later on in the week, or maybe today. I'm actually not sure about the schedule. Okay, so hopefully it'll be helpful in that sense too. So what I'm going to do is shown here. First, I'll give a perspective on how we even choose what to grow. I think probably most everyone in the audience is aware that we, right out the gates have a huge problem, and that is that the chemical structural phase space is so enormous that no sort of brute force approach can actually cover all of the space that we need to cover. Right, so that's a big problem. It's also a big opportunity. Well, once we choose something that we want to grow, or at least the general direction we want to go in, we have to actually do it. And a good starting place for thinking about that is to consider what sorts of chemical phases are actually available, what's known about them, and sort of what can come out in these mixtures. A good way to start on that is to think about binary phase diagrams. So I'll do a rundown of the basics of how to think about binary phase diagrams, and then extending that to ternaries. And then, once you've done that work and you know a little bit about, what might happen in a reaction, then we can think about what synthesis methods could be most appropriate for the particular thing that you want to grow. So I'll drill down there on two particular methods. All right, so that's where we're going. And the first statement that I want to make is that, the reason that we're so excited about quantum materials is sort of twofold. I think it's fair to say that each class of quantum materials is really its own universe for the electrons that are living inside of it. Okay, and what does this mean? Well, it means that those wave-like electrons that are existing inside of a solid are interacting with any number of other factors, like spins, the structure itself, orbital degrees of freedom, so on and so forth. And in each case, these different factors are going to combine together to produce novel phenomena. And of course, some of that phenomena can be useful for some things, we hope, but also when really remarkable phenomena fall out, this also pushes back the boundaries of what we actually know about nature. Right, so that's why we want to study these types of materials. There have been many successes in the past. You can sort of break them down into two broad categories. You might say that there are classical quantum materials, such as conventional superconductors, semiconductors, permanent magnets. They've all been put to use in a huge variety of technologies. And I also don't want to imply that this area of science is sort of done. It's not. There's still many advances that can be made there. But looking forward, we can also think about next generation quantum materials. And that would include many other things, right, that are attracting lots of interest, like materials for qubits, quantum teleportation, quantum sensors, two-dimensional electronic systems. My own special area of interest is materials with strong electronic correlations. And then when they intersect with things like topology, frustration, so on and so forth. Right, so interesting science and lots of fantastic applications. Okay, but that doesn't actually help us to make a decision yet, because still there's so many phenomena that we could study, and there's so many materials that we could study. So we have to adopt a philosophy of how to choose what to grow. And I think that most people do follow this path, and it's a rational path. And it's just that you would choose some sort of degree of freedom and try to pursue it. Okay, and just to give a example of that, you can look, for instance, at the history of F-electron materials. And here's a timeline from the mid-20th century to the present. The most straightforward thing that you could do is to think about the F shell and realize that it could give you very strong magnetism, maybe very strong anisotropic magnetism. And indeed, that's the case. We get materials like samarium cobalt 5 and the neodymium iron borides that are essential for technologies, and many other strong magnets besides. But there's a really important point here, and that is that although choosing a degree of freedom makes sense, and it does lead to discoveries like this, it really doesn't guarantee a straight path. Right, and you can see that in the F-element systems where just multitudes of other types of behaviors emerge, and many of them totally unexpected. And this includes things like electronic hybridization, mixing between the F and the conduction electron states. Prior to the 70s to 80s, I think this would not have been expected. But since then, it's been the root of sort of a whole field of physics. And even today, with the discovery of Lazarus superconductivity in uranium tellurium-2 by folks that are, at the school right now, we see this as still a very vibrant area of research with many unanswered questions. Of course, there's other unconventional superconductors that come out of this, and just many other exotic electronic and magnetic states. Right, so the message that I'm trying to make here is that when we're thinking about what to do, we choose a direction, but then we have to leave room open for serendipity to intervene, because it's almost inevitable that it will. Okay, so next statement is that sample quality matters, okay? We can see this, repeatedly in different instances. A good one is that, the discovery of the quantum Hall effect really only came from making very high purity samples. But it's also fair to say that we still don't have a very good understanding of what happens in intermediate or strong disordering situations. Right, so in any case, for any material we think about, and I guess a good example was just seen for the nickel oxide superconductors too, the nature of the disorder or sample quality matters, and we have to pay attention to this. Another great example is seen for uranium tellurium-2, the history of which is summarized here, where we have resistivity on the y-axis and temperature on the x-axis. And let me pull out my little pointer, if I can, so I can be really clear about this. Okay, so the earliest studies on this material, for example, by 2006, were on materials that were grown by a flux method, as far as I understand. And I'll say what a flux method is a little bit later on. In any case, it produced samples with resistivities that look like this upper gray curve. And you might conclude that these are having a lot of disorder in them because the residual resistivity at low temperatures is large. And there's absolutely no evidence for superconductivity. I think these guys did what any reasonable person would do. They saw this result, they reported it, and they moved on. But as far as I understand, the next step came in 2019 when Sheng Ran, JP, Nick Butch, and some others happened to produce this same material using an iodine vapor transport method. Okay, there was an instance, I think, of serendipity and high quality samples sort of co-occurring. This produced samples that have these lower residual resistivities and incredibly the onset of superconductivity, which has now kicked off this intense period of research. And then further work has been done to improve sample quality that has impacted the superconducting transition temperature as well. All right, so all of this just to say that, you know, we do have to think about the impact of sample quality, how to control it. And, you know, this gives an example of a regime where having very clean matters, but it's also the case that studying more disordered is certainly an active topic. Okay, so that's enough about philosophy. Just to summarize, I think there's a real challenge in developing new materials, but at the very least, the discovery of extraordinary phenomena requires developing a familiarity with fundamental degrees of freedom. In other words, just choosing a direction that you want to go in. But once you do that, you really do have to connect your knowledge about chemical, structural, electronic, magnetic, and other trends with what you actually know about real materials in the chemical structural phase space. And amongst all of that, an ongoing commitment to quality. Right, so what does this really mean? It means this isn't a single discipline activity. It's really a place where physics, chemistry, material science, and now probably data science and who knows what else need to converge and work in harmony. Okay, so it's a jack of all trades type of work. Okay, so now I'm going to switch gears and talk about something or some things that are more specific. And before I do that, I just want to bring your attention to some useful references. These are, I mean, there's many references out there that you can get, but I especially like these ones. This book by Brian Pamplin is actually from the 1960s or 70s, and it summarizes so much of what we want to know about crystal growth. There's also this fantastic book that was published a few years ago from the FQM workshop that I think is very useful. And then finally, I want to bring your attention to a book like this Hawley's Condensed Chemical Dictionary. The reason this is useful is that it actually tells you something practical about a wide variety of elements and chemicals. I don't want to say that you shouldn't look at or have MSDS data sheets. They're important, but they're also not extremely, I don't know, they're not very frank, right? You could read any MSDS data sheet and start to believe that any material is extremely dangerous. Having a book like this, on the other hand, lays it out in a more practical way. I also want to encourage people in the audience, if they're going to begin a new type of reaction, working with new elements, it's always a good practice to talk with your advisor or to talk with other experts in the field. I'd be very surprised if you were to reach out to someone like me or a different crystal grower and we weren't very open to talking about, you know, how to be safe dealing with these different sorts of things. So please feel free to do that. Okay, so now let's start getting down to the details. You know, what we have to work with is the quantum materials foundry or the periodic table. And I'm going to make an analogy that Paul Canfield likes to make, which I think is very appropriate. And that is that when we think about the periodic table and the degrees of freedom that are available there, we're going to get different flavors, from different parts of the periodic table. So just to summarize that, and of course you could think of other trends too, you'll see that, for example, if you look on alkali metals and alkaline earths, what you're going to wind up doing is to tune the unit cell size and accomplish band filling. And that's going to be completely different from what you would do amongst transition metals, where instead you're going to tend to more do things like tune the density of states and access magnetism. And that'll completely contrast with what you would get elsewhere, like amongst light elements like carbon or boron, where instead you're going to get strong bonding, high phonon frequencies, so on and so forth. Right, so when you're setting out to think about what type of behavior you want to create in a material, you need to think about what flavors might go together. That's what you can do if you're good. If you're incredibly creative, you might also think of flavors that you wouldn't think would go together, but actually make a new and exciting dish. Right, so that's how we want to look at the periodic table. But of course, that's only half of the story, because we also have to think about the chemical trends. We can't just arbitrarily make any combination we want. And again, here, there's different behaviors in different parts of the periodic table. For example, alkali metals and alkaline earths tend to be air sensitive and easy to melt. And in contrast, transition metals will be only kind of air sensitive, but much harder to melt. And don't forget that amongst these, there's even refractory metals like tungsten, or iridium and others that have very high melting temperatures, don't like very much to combine with other things, and are just generally difficult to deal with. All right, so imagine trying to combine an alkali metal with some of these guys. Not so easy. Okay, we have other personalities elsewhere. Boron and carbon don't like to melt or dissolve into things, but they're super abundant. So wouldn't it be nice if we could use them all the time? P-block elements tend to be or can be poisonous and have high vapor pressures. Other ones are pretty easy to melt. They like to react, but some of them are pretty poisonous. Beware of thallium. Okay. And then, of course, other properties in lanthanides and actinides are a whole other deal. But, uranium and thorium are more or less fine to work with. All right, so we have to be aware of these behaviors. We also have to be aware of how pairs or groups of elements will interact with each other. So it's certainly not the case that we can just make arbitrary combinations of elements. And one of the best ways to see that is to start thinking about binary chemical phase diagrams. So I'm going to spend a few slides on this. For your reference, I'd really like to put you in the direction of this great article by Paul Canfield as well. And in fact, the figures I'm going to show you are taken directly out of there. So for a second read or to try to process this further, definitely go there and have a look. Right, and I also want to mention that there are a very large number of binary phase diagrams that are available. Usually through a university, you can see them through something called the ASM database, but sometimes departments will also have these large sort of tomes that you can page through and see, see the data as well. There's one further thing that I want to tell you, and that is that although you can look up binary phase diagrams for any number of combinations of elements, you really shouldn't take them as the final word on the subject. And the reason for that is that in some cases, they were generated experimentally. In some cases, there was some modeling that's involved. I think more or less in most cases, there's a lot of interpolation going on. So the exact location of phase boundaries, the exact location of phases, and even the question of whether or not all of the possible phases are included, I think are debatable in almost any case. Right, so if you look at a binary phase diagram, take it with a sense that there may be more to find out in there. It's more of a guide than a hard and fast rule. All right, with all that in mind, let's have a look now at what do we mean by binary phase diagrams. So shown here is some made up arbitrary combination of elements A and B. Okay, and on the y-axis, we have temperature, and on the x-axis, we have the relative compositions of elements A and B. So the numbers on the x-axis are actually a little bit confusing because when it says 0, what this means is that it's 100% A. And when it says 100, it means it's 100% B. This is the atomic percent of B going into A. Okay, so there's some other features that we can notice on this phase diagram in different lines. You have these non-monotonic lines that trace out on the top of the phase diagram. You have these vertical lines, some of which connect all the way up to this boundary and other ones that don't. And then you have these horizontal lines. Okay, so what are these different things? Well, the first thing is that the non-monotonic line is just a line that connects the liquid phase to the solid phase. Okay, so all of these lines represent the phase boundary between the liquid and the solid. Okay, so fair enough, that's not so bad. The other lines, for example, AB, that extends all the way up to the melt, this represents a phase that forms out of the melt. This is a compound. And the fact that it connects all the way up to the melt tells you that this is a place where if you exit the melt at this stoichiometry, you'll form this actual phase. Okay. In contrast, you'll see that A2B doesn't connect all the way to the melt. Instead, it terminates, before it reaches the solid liquid phase boundary. And what this means is that this material, if you were to take, some A and some B in this ratio and press it together into a pellet and then react it at a temperature below this horizontal line, it would form this phase. But if you heat above this line, it'll decompose. Okay. And there's one more thing that you should notice in these phase diagrams, and that's that there's places where they go through a minimum. This is very convenient for various types of growths, and what this is called is a eutectic point. Right, so just to say that all again, the vertical lines are congruently melting phases. They form directly from the melt. Ones that don't reach the phase boundary are called incongruently melting, or they undergo peritectic decomposition. Lots of words here. We have a eutectic point, which is a minimum. Okay, and that's what we have in these sorts of phase diagrams. All right, so now just to give you a specific example, let's go ahead and consider the phase diagram combining cerium and tin. Right, and you can see all of these features in play here. I especially like this phase diagram just because there's so many different cerium-tin phases, right? Telling you that cerium and tin, depending on their relative composition, like to bond in all sorts of different ways. So it makes a really rich phase diagram. I do want to point out that there are other combinations, not of cerium and tin, but of other elements that have absolutely no phases in them, right? In other words, no bonding occurs. And this on its own immediately gives you some insight when you're thinking about whether or not a particular thing that you want to grow will actually form. In other words, it might be a problem if there are just a tremendous number of binary phases that want to form. In other words, there's all sorts of energy minima that can produce these compounds that might circumvent your ability to produce the thing that you want to make. On the other hand, if there's absolutely nothing that forms in the space, maybe you can put this to work to your advantage, but it also might just mean that the combination that you're after really is not one that's going to form because those elements don't play nicely together. Okay, so what else here? Well, let's just point out a few things. There's some examples that are line compounds extending up to the melt. There's some examples that are peritectics that don't make it all the way up, right? Like cerium-3 tin. And then we see a few eutectic points hanging around in the phase diagram. Okay, so that's a binary phase diagram in a nutshell. So what else can we do with it? Well, it might be, that we want to grow these particular phases. And, in this generic phase diagram, we have phases A2B and AB. And, we could make A2B by heating some powder in a pellet and make a polycrystal, as long as we stay below the paratectic phase. But that also might not be so great if we were wanting to grow a single crystal. So how can we grow a single crystal? Well, the short answer is that we can grow it out of an excess of element A. Right? And this is sort of your rudimentary principle when you're thinking about what a flux growth is. And we'll return to flux growth a little bit later. All right, so if we're in an excess A, we're going to be where this black arrow is. If we heat this combination up into the melt and then slowly decrease temperature and cross this phase boundary, what's going to happen is that because it's connected by this horizontal boundary, we'll begin to drop out this A2B from the melt. If we do it slowly enough, it'll form single crystals as it comes out. Also, we'll be depleting the melt of B, so we'll be moving to the left here. The melting temperature will lower, and as a result, as long as we're slowly decreasing temperature and we don't exceed this eutectic point, we're going to be able to continue to form this phase directly out of the melt. This approach can also be applied for the AB phase. Now, it might not be that you need to, because you can directly access the melt and then cool it down and get AB. But let me point out one or two things that might get in your way. So one is if this upper limit for the melting line is just too high, right? Your furnace, I don't know how it goes, but if you have a regular silicon carbide heating element, you're probably not going to take it above, most likely you'll be running at 1200, you may go to 1500 C. If you can't reach that temperature, then you need a different strategy. The other thing that's important to point out, and we'll return to it a little bit later, is that the way that you cross this phase boundary determines whether or not you produce a single crystal or a polycrystal. And controlling that interface is pretty challenging. Okay, so how can we get around this? Well, again, we can go to an excess A and ride down this solidification line. If we do it on this side, we're going to drop out A2B as well as AB at some point. But an even better strategy would be to go to an excess of B and simply ride down this solidification boundary. Okay, so this helps you to start building a strategy for how you could produce a particular binary phase. The advice that I usually give people is that if you look at a binary phase diagram and you see that you can start building strategies like this, the best thing to do is probably to try a few different concentrations, because there's some additional details that almost always intervene that determine whether or not one strategy is better than another. Another consideration might be that your A is a very expensive element and your B is an inexpensive element, right? You can think about things like that as well. Okay, so that's our binary phase diagrams, but of course we generally want to grow even more complicated things than that. So it's useful to think about ternary phase diagrams. But these are much less well developed in the literature, and they're more difficult to interpret. But I want to give you a perspective on how to at least get started in thinking in this way. So what we have here is an isothermal slice just between generic elements A, B, and C. Okay, and we're just at some constant temperature, and then we have this grid showing relative concentrations between them. And if you want to get started on this sort of thing, and you don't have a good literature search for a ternary phase, what you can do is just take your binary phases and lay them on their side like this. And while this doesn't tell you a whole lot about how the different isothermal slices are really going to work, what it does do for you is to give you a starting point, right? You may decide to I don't know, sort of situate yourself in a certain part of the phase space in order to avoid, a very large number of other binaries that might appear somewhere else. Okay, so this type of strategy can be fruitful, but it takes some creativity and guesswork. As long as we're on this subject, I want to show you one other thing that I think is just really interesting. And that is that sometimes, well, as you might expect, you get some useful eutectics in these ternary spaces. And one that I just think is great and a lot of fun is something called Gallinstan. It's a mixture of gallium, indium, and tin. Gallium, of course, melts close to room temperature, but indium and tin melt above room temperature. But it turns out that at this particular combination, the solidification boundary is actually quite a ways below room temperature. So I want to show you a quick video here just to illustrate this. This is some Gallinstan that we made on a hot plate. And sure enough, at room temperature, it's a nice liquid metal. Okay, so this is not just for fun, although it also is just for fun. What can you do with this? Well, for one thing, it's great for educational purposes because we can't bring mercury to, K-12 schools, but you can bring this to K-12 schools. The second thing that I think is really interesting about this is that it's a very useful low temperature flux that you can do crystal growth in. Right, so something that we do in my group is that when we work with undergraduates, we want to ramp them up kind of slowly. It's a little bit hard to ask an undergraduate to use a hydrogen-oxygen torch on their first day. But you can ask them to make Gallinstan on the benchtop. And with a little bit of work, you can also teach them how to use like an acetylene torch or something you can pick up at Home Depot to work with Pyrex. Right, so in this way, you can enable some pretty low temperature and relatively safe types of crystal growth experiments. There's one other thing that I think is interesting to think about, and that is whether or not you can do crystal growth below room temperature, and whether or not the ways that crystals form will produce novel phases. So I thought I was being fairly clever a few years ago, and we did a crystal growth in Gallinstan, or just with Gallinstan, in a PPMS or an MPMS. I can't quite remember. In any case, it turns out that you can observe that it does superconduct. We were going to take this a step further and see whether or not we could identify what phases had solidified, but it turned out that someone had beaten us to the punch on this, right? But at least it opens a new way or an unconventional or unusual way to think about crystal growth, not at high temperatures, but at low temperatures. And how might that produce other unusual phases? All right, I've gone on for long enough about this, and I'll just move on. Okay, so that's our...
Ryan?
Yes.
I just want to stop and see if there are any questions.
That would be great.
Any questions from the audience? Yeah, just talk loudly. I'm not sure if he'll hear you, and I'll repeat it if necessary.
So I was wondering if there's a usual way, if you grow out of excess A or excess B, is there like a typical way to remove the excess A or B, or is that very specific to the material?
So let me rephrase the question and just be sure that I've got it. I think that the question is there a typical way to remove the excess material? Is that right?
Yes, for like the binary.
Yes, so that's correct. There is a typical way, although there's more than one way. And I'll show this in a few slides. But for our flux growth methods, I and many others will use a centrifuge. So we'll typically invert the ampoule. There'll be some sort of material that can allow the excess material to pass through it while it's still liquid, and in that way separating the crystals from the flux. Now, to be honest, there's other ways. You could, if your flux was a relatively high vapor pressure sort of thing, you might be able to remove it by placing it in a temperature gradient and letting it just sort of transport away to the cold end. And still other times, you know, if you can't find a good way to separate the crystals and the flux, you might just break it open. Sometimes you can just cleave them out. Does that do the trick?
Yep.
Okay.
Yeah, Stan?
Hi. Hey, Ryan. I
Hey,
see
Stan.
logo there. That's good. Question on the growth that the flux growth we're talking about. You also indicated that with the uranium telluride that it provided or resulted in worse crystal quality compared to the other methods. I mean, this is a good way to, I mean, not grower, but it's a great way to grow materials. But what would allow flux growth to provide cleaner crystals that might show oscillations, or do you need to go to the more exotic techniques?
Yeah, no, that's a very good question. I think the first answer, which is not especially helpful, is that it depends a lot on the particular material. So in the case of uranium tellurium-2, you know, my understanding is that first of all, sorry, we don't have a very good understanding of what makes it a quote unquote low quality or high quality sample. But it is true that if you grow it in a salt flux instead of a tellurium flux, this somehow produces the higher quality samples. More generically, you know, it might come down to questions about making sure that your flux elements are extremely clean to begin with. It might have to do with thinking about your crucible and being sure that you're not leaching any of your crucible out into the melt. That might take some, you know, studying or experimenting with different types of crucibles. It might have to do with being sure that the environment, the gas environment, is really super clean. I think in every case, you have to fine tune this, you know, for the particular material.
Okay, any other quick questions? Okay, no, let's keep going, Ryan, thank you.
Okay. Hey, JP, I made the mistake of not having a timer by me. How much more time do I have?
You have about 10 minutes and then there'll be 10 minutes for questions.
Okay, I'm gonna move fast. Okay, so with the binary and ternary and strategy stuff in mind, we now can choose a crystal growth technique. And of course, there's many to choose from, right? We have things like solution growths, which would be like our flux growth. There's different types of fluxes available. Vapor phase transport, thin films, 2D layering and stacking, and melt growths. I don't have time to discuss all of these. Hopefully some of the other ones will be covered this week. What I especially want to focus on are molten metal or just general flux growths, and then direct melts like arc furnace, Bridgman, Czochralski, and so on. All right, so here we go. Let's start with direct melts. There's any number of ways to reach a high enough temperature where you can melt a combination of elements. This includes things like a regular resistive high temperature furnace. Okay, of course, there's different types of high temperature furnaces, but let's not worry about that now. There's things called arc furnaces. There's induction furnaces. And if you can achieve all this, then the next step that you do need to think about is how to control the interface between the melt and the solid. And a common way to do that is through something called crystal pulling, or the Czochralski crystal growth method. All right, so direct melts. They're also, I want to be very clear, not useful for paratectic phases, right? And the reason is that we have this deep composition region that's going to promote the growth of all sorts of other phases that you don't want. All right, so let's think about direct melts. A very useful method that you're going to see during the practicals is the arc furnace method. That's shown schematically here, and in reality, on the right-hand side, where you have a bell jar, you can introduce an inert gas like argon, and then into this space, you'll insert what we call a stinger that's attached to a welding power supply. And then using this, you'll be able to discharge an electrical arc through your sample down into a hearth which is usually something like a water-cooled copper plate. And that's shown in the lower right hand here. Okay, so this is the general idea of how an arc furnace works. I'd like to show it to you actually in action now. So that's shown on the video on the left-hand side, where we're going to strike an arc, and we're going to bring it into contact with a piece of zirconium metal. There's a few things that are worth pointing out. First is that zirconium has a pretty high melting temperature, but you'll notice that it takes almost no effort at all to melt it using an arc like this. You'll also notice that the size of the sample matters a lot, right? We're limited by the size of the arc itself, and as a result, sample size that you can actually deal with is defined in this way. Right, so we can watch this thing sort of make its way into the copper pot. There's one more thing that I want to show you here before moving on, and you'll see this when the arc turns off. That flash is just the optics changing the darkness. But the main point here is that when we had the arc on this thing, it was at very high temperatures, even above 2,500 C. And it cools, down to below 600 C in a matter of tens of seconds. That's a very fast cooling rate, okay? And what it tells you is that you really don't have very much control over the liquid to solid transition in this type of reaction. And as a result, you can expect that arc melting will produce polycrystalline samples, generally speaking. Right, so that's what this method is for. It's very fast. It's very good for rapid throughput reactions. It has a few other applications as well. These are shown in these little extra panels up here. So let me bring my pointer back. And what we're showing, first of all, in the first two images is just a metallic powder, and then we've arc melted it. So the reason that we would do this is that if you have a metallic powder and it's been left out on the bench, there's a very good chance that it's picked up some junk from the atmosphere. Okay, even if it says it's high purity, probably not. Okay, unless it was stored properly. And what arc melting does for us is it not only forms this into a nice little ball that's very manageable, but it also kicks off a huge amount of material that's seen in this halo here. So it's a good way to sort of clean up your material at the beginning. The other thing that's important or useful is that we can use an arc furnace to produce crucibles, right, of various sorts. And what's shown here is a tantalum tube that was shaped into a nice crucible using arc furnace welding. If you want to know more about that, just contact me and I'll tell you the nitty-gritty details. All right, are there any other considerations? Well, sure. You do need to be able to melt the material. In other words, melting two pieces of semiconductor things, like some silicon and some carbon, probably isn't going to work too well. But if one of the two things will melt, like if it was iron and silicon, that'll be fine. To get around this, you can sometimes use a conductive container to transmit heat. You should also avoid high vapor pressure elements because this is such a violent process that it'll just vaporize them. And then some elements like manganese actually turn out to be a pain. And this is because dirty manganese doesn't shatter when you put an arc on it, but clean manganese does. So in other words, if you arc melt it once, it tends to go well. If you arc melt it twice, it tends to shatter. And I don't strictly know the reason for this, but I think it has to do with the different ways that the thermal expansion works in a dirty piece or a clean piece. So there's a lot of tricks of the trade, and you can learn about that if you just ask around and talk to people. Okay, but we can heat materials in other methods too. One that's really fantastic is induction furnace melting. The schematic for that is shown here, where we have a copper coil. This is tubing. It's water cooled to manage heat load, and it's connected to an RF power supply. That RF power supply generates an electrical current in here that in turn produces a oscillating magnetic field along the axis. And if you insert a metallic workpiece into this, that will couple to it, drive electrons around, and result in resistive heating. And that's shown in practice on the left-hand side. So what does this accomplish? Well, it gives you very localized heating. it gives you very controllable heating because you control it with the amount of power that's being applied. You can design temperature gradients. And so in that way, it's very customizable. In addition, the RF field provides stirring of the melt, which can help your reactions make their way in the right direction more rapidly than just regular thermal mixing. It's useful for metals and non-metals because all you really need to do is to couple to the crucible that you're going to hold your material in. And then depending upon the shape of coil that you make, you can access a wide range of different temperatures. And the final thing that I really like about this is that it gives you great flexibility in terms of the shape of the crystal growth environment. So here we've wound it around a quartz tube. It's on the outside of the quartz tube. You could just as easily imagine putting it on the inside of the quartz tube or inside of a high vacuum system. Or even, I've seen a case where someone had a high vacuum system. They had a platform inside of it with some crucible or something that they wanted to heat. They placed their coil outside of the window, right, just out in air, and they were able to use the magnetic field that was generated in that way to couple inside of the chamber and heat their sample. Right, so lots of flexibility. The other thing that I haven't mentioned, and I'll just show this quickly because I am running out of time, is that this can be used for levitation, magnetic levitation. So an example of that is shown here, where we have a coil where we actually have a counter wind on it to stabilize the levitation. And as you can see, it's really no problem to levitate a piece of aluminum. Ultimately, what you need to be able to do to levitate denser things is to have a high enough power supply and a tight enough coil. All right, but we'll just move on from there. And then the other thing that I did want to say is that, we do need to think about crucible types. They need to be conductive. A nice type of crucible to use here is a sealed tantalum crucible. Okay, but many others are available. Regarding configuring these things, you can also even use them for Czochralski growth, where what we've done is to place a graphite crucible in here, produce a melt of something inside, and then insert a pull rod into it. And in that way, we can pull crystals out of the melt, like the one that you can see emerging here. And I guess I should bring my pointer back. You can see the crystal emerging from the melt. And generally, you can produce things like those shown on the right-hand side. Okay, so that's direct melts. Now let's take the last little bit of time to talk about crystal growth from liquids, right? And just to set the stage one more time, we talked about binaries. Another great generic example is how you grow sugar crystals in water, or borax crystals in water, or even alum crystals in water. These are all things you can go and pick up, at the store, great for demos, so on and so forth. But more generally speaking, or for our purposes, common fluxes include things like salts, low melting temperature elements, or binary eutectic mixtures. And really, the world is your oyster in choosing what you want to do. Okay, so in practice, what do we actually do? Well, we want to take some crucible to contain the materials in. A very common crucible is aluminum oxide. The reason that people like to use this is that it's relatively cheap and it tends to not interact with melts, although it's not a 100% guarantee that it will remain completely inert. In other words, for some melts, aluminum, or possibly even oxygen, I guess, can leach out into the melt and change its composition. That's just a word of warning. If that happens, you need to think about other types of crucibles, or maybe it will produce exactly the thing that you want. Okay, once we have our material weighed out in this way, we'll generally want to protect it from atmosphere as we heat it. A very convenient way to do that is to seal it inside of quartz tubes, as shown here. We do that using a hydrogen-oxygen torch that I think you'll see in the practicals. It's worth mentioning that there are these things called Canfield crucibles. And this goes back to the question of how do you separate the melt from the crystals? Well, this is one way to do it. And the idea here is that your reaction would occur in one of these crucibles, And then you'd separate it from a catch crucible by a fritted disc of the sort that's shown here. Okay, and these just go together. You'll see why we would do this in just a second. So we have our ampoule. We can take this thing now, seal it, and place it inside of any furnace that we like, right? Take it through a heating schedule that goes into the melt and then slowly decreases temperature such that we cross one of these solidification boundaries. When we're done, we want to take this out of the furnace while it's still hot, and so that the flux is still in its liquid state. We then invert the crucible, place it inside of a centrifuge, and spin it hard. The result is that the flux will pass through the fritted disc and crystals will remain in the growth crucible. And in the end, if you're lucky or good or experienced or any combination thereof, or even just lucky, I guess, you'll produce nice, beautiful crystals. Here's some examples. One further thing that I want to point out that's really extremely useful about doing crystal growth this way is that crystals usually form with well-developed facets, like the ones shown here. And the facets are going to be along some well-defined crystallographic direction, which is something that you need to know for the experiments that you'll do later. All right, so I think that I more or less made it in within the time limit. What we've done really is to talk about the first step in a longer process that's required for studying these types of materials. Generally speaking, most everyone is following a make, measure, and tune process, right? And then repeat. On the make step, there's any number of ways to proceed. And I also want to emphasize that even on this step, there's all sorts of science that we still don't understand very well. We've just barely touched on some of it today. So just to quote Winston Churchill, both for this cycle and for understanding how to do crystal growth, although I'm sure he wasn't thinking about crystal growth, this is not the end. It's not even the beginning of the end, but it is perhaps the end of the beginning. And even that might be optimistic. All right, so here's my perspective, and then I'll be done. I think that the search for new quantum materials is exciting and unsolved. This is both in the space of how to produce them, how to decide what to produce, and then to actually understand the ones that we have. In order to make progress, we have to let serendipity and materials refinement work together. Also, it's a truly interdisciplinary activity, and no one group can actually solve this whole problem. I also like to point out that this is a fantastic training ground for the next generation of scientists and relative newcomers, right? And the reason for that is that there's just so many stages to this, different nodes for people to attach to, and then grow out, into more and more sophisticated topics. And finally, I just always like to say that crystal growth inspires awe and excitement, which is fuel for discovery. It's definitely the case that if you are doing a growth, when you take those samples out of the furnace, it's a little bit like Christmas morning because you really don't know what you might have in there. So that's exciting. All right, so that basically brings me to the end, and I'll be glad to take any questions now.
Thank you, Ryan. That was great. Okay, we're open for questions. Yeah. Speak loudly, please.
When it comes to growing using the flux method in a furnace, what would the effects be of pressure, for instance, zero pressure in a vacuum furnace?
That's a good question. So the question is, what is the effect of pressure during a flux growth? And again, I think this would come down to the details of the growth itself. So where to start with this? I mean, in some cases, I don't know if it would matter very much. So for example, if there's hardly any vapor pressure above the melt, so for example, if you have some combination of elements, you heat them up and they don't want to evaporate very much, I don't think that having a modest pressure on there would matter hardly at all. But it could happen that you have a melt where some of your elements do want to evaporate. And having some sort of modest pressure to hold them down probably could be useful. There's probably even another regime that I wouldn't encourage you to try to access with quartz tubes, where it might be a very high pressure regime. And that possibly could impact the thermodynamics of how the growth works. But I don't know. I don't have any experience in that regard.
So I can add a quick thing on that. So just to paraphrase, between vacuum and ambient pressure, there usually is not much difference.
Yeah.
If you think
That's-
about going to higher pressures, tens or hundreds of bar, gas pressure, that could tune the vapor pressures such that melting points will change.
Right. And
So totally,
I don't, sorry, go ahead.
go ahead, I'm done.
I was just going to add that I don't know of a lot of works that go to very high pressures, although there was a series of experiments that I did when I was a graduate student when we were using a cadmium arsenic flux. And this was a nightmare because the pressure above the flux gets large. So we had to actually build a system. This was more a matter of strategy than influencing the crystal growth, but we would seal the material in a quartz tube. We would have a partial pressure in there that would counterbalance the cadmium arsenic vapor pressure. And then outside of the quartz tube, we had another steel tube that we loaded with partial pressure so that it would counterbalance the pressure that built up inside of the quartz tube. So certainly it can come into play when you think about strategy of how you will do something.
Other questions? Yes, first and then you.
Can you talk a bit more about the tantalum crucible welding? Because you mentioned that it's like in the arc melter, and from my understanding, it was that you were putting your reactants into the crucible and sealing them there. So how do you prevent them from reacting in that first step of welding the tantalum?
Yeah. Okay. So I think the question is, when you're using a tantalum crucible, you have to seal the other end at some point. Or, okay, you may want to seal the other end. So how do you avoid having the elements react with each other during that process? Is that right?
Yes.
Okay. So two statements. One is that you may not have to seal the other end with a arc. So it's depending on what environment you're going to put that tantalum crucible into, it may be sufficient to simply clamp the other end and bend it, right? And that might be fine if you were going to place that tantalum tube inside of a quartz tube and then seal that under vacuum. So no problem there. But one of the main reasons that you would use a tantalum tube is that you might want to go to a temperature that's much higher than the melting temperature of quartz, right? So you wouldn't be in that situation, but instead you still might take your tantalum tube and put it in some sort of gas flow circuit that has inert gas going in it, and then place that inside of a tube furnace or something like that. So there are cases where you can get away with not arcing at all. Okay, but if you do need to arc, here's the trick. So you need to make sure that your tube is long enough and that the material that you're placing in it is far enough away from the hot end where you're going to be putting the arc. So something that is about as long as, what I'm showing in the image here is long enough in most cases. And then what you do is you clamp, deform the end so that it's nice and flat. There's a way to bend the tips of it so it kind of makes a fishtail that's bent up. I could send you a picture of that if you're interested. And then then the advice is to move fast, okay? So you don't need to have the arc on the part that you want to weld for very long, and you simply run it across the edge of that tip, let it cool down, then you run it across the edge of the tip again, let it cool down. And those processes will take, you know, maybe 5 seconds. And that's fast enough to avoid doing anything to the material inside. If you're really worried, you could also build a clamp that is screwed into the copper hearth itself and attach that clamp, you know, to the end of your tube so that the tantalum and, you know, by extension, the material inside of it is thermally sunk down to the copper.
So there was a question here?
Just going back to the binary phase diagrams, how do you know which element to use in excess?
Yeah, so in the binary phase diagram, how do you know which element to use in excess? So you have to look at, I wonder if I can get back to it. Let me see. Oh, shoot. Okay, there we go. Let me see if I can get back to it. Here we go. Okay, can you see that? Okay. So I think the real answer is that you would try a few things. But if I was wanting to grow A2B, it would probably be, well, it would be pretty straightforward to make a decision because I'd like to just connect with this horizontal line. And so I should be over here in an excess of A. If I wanted to grow AB, you know, it's not quite so obvious because there's 2 ways to get there. But what I would prefer to do, I think, is to go into an excess of B. And the reason is that there's just nothing else that's going to intervene or interfere with this process. If I go on this side, you know, I do have this A2B phase that's probably going to be in play. And then as for how to choose the actual composition, my advice to myself and other people usually is just to try a few different places to work.
Any other questions? Up here first and then.
So for the flux, is it necessary to have a homogeneous mixture with the flux and the material? Is it necessary to have homogeneous?
Can you say that one again, JP?
Sure. So the question is it necessary to have a homogeneous mixture for the flux growth, flux and material itself? You mean at room temperature before you start?
Yes.
Yeah.
Is it necessary for it to be well mixed when you start? So no, it's not. So when I do flux growth, I'm usually, in fact, I prefer using chunks of material. Now, I am concerned with ensuring that it does all get melted, right? And you could imagine, so one of the things that's difficult about flux growth, or still not extremely well understood, is all the intermediate steps, right? Like what sorts of intermediate phases form during the warm up and the cool down. So in order to try to stack the deck in my favor, what I like to do is to put some of the flux on the bottom of the crucible, put the reactants in the middle, and put some of the flux on top of the crucible. And that way, as it melts, it has an opportunity to sort of be encompassed, you know, by the flux itself. But the idea is that, you know, regardless of how you stacked it in, hopefully when you get up into the melt, it'll all dissolve in and become homogeneous. Although I do also have a suspicion, but I don't know for sure, and that is that if you get into the melt, depending on your temperature, it might be that there are also some types of sort of preformed bonds that are going to hang around. I've certainly seen that the path that you take in your heating curves can impact the types of crystals that come out. So there's a lot to this that is not quantitatively understood.
Okay, there was another question. Yeah.
Yeah, I've heard before that salt can affect melting points. Is that true generally, or is that just the effect of the salt flux in the mixture that they're?
Can you say that one again too, JP?
The question was, you heard that salt?
Like having a salt present or salt flux present can affect melting point.
Can you be more specific, like salt within another flux material?
Sodium material, and say you're saying just sodium chloride, salt flux, and then you want to reach this point in the phase diagram where everything's melted. I've been told that sometimes that point can be lower. So say the TC is down by 100 or so Celsius.
Because you,
because of the presence of the salt or the flux.
you mean in comparison to a metal flux or some other flux?
So just the material without the salt presence.
Oh, I see. So the question is the presence of the flux material, the solvent, can change the melting point of the material. And is that true? Yes.
Does it mean can it change the melting point of the material after you've made it? Is that what the question is, or does it change?
Okay, so maybe I'll paraphrase again. Is the question that if you take, I forget AB, but compound CD, and you just heat it up and it melts at 1,000 degrees, now you put it in a salt flux or some other flux solvent, and it reduces the melting point
of the whole mixture.
Of the whole mixture, yeah. Yeah, that's the whole point of the phase diagram, yeah.
Absolutely. Yeah, that's part of the fun. Yeah, that's absolutely part of the fun. Yeah, that's definitely what's going on.
So just looking at this phase diagram, if you take compound AB and you add a little bit of A, you've moved the melting point, right? Or the example we often use is sodium chloride salt. I don't know what its melting point is. It's probably 2,000 degrees or something. But you put it in water and it dissolves. So melting point is, depends what you mean.
That's a great example. But so there's one other interesting thing that oh, sorry, go ahead.
Go ahead, Brian. Yeah.
I wanted to mention too, this just made me remember that sometimes it may also be interesting to take crystals that you already have and to use them to seed a melt, right? So sometimes if you have some little tiny crystals and then you put them into a flux where you want to grow larger crystals of that sort, by seeding it, you may, if you're careful about how you heat it, that takes some figuring out, you may be able to use those as places where you'll nucleate, better and thereby produce larger or higher, maybe higher quality samples.
Okay, so one more quick question.
Yeah. So when you're using flux, like salt flux, where the flux itself is not a part of the final compound that you're trying to get, can you decide how much flux goes in compared to the?
That's a good question. I think the honest answer is kind of you try some things. My general procedure is that I like to try 1 to 10, 1 to 20, and 1 to 50. I don't think I have a better answer than that.
Yeah, if you don't have the phase diagram, it's really hard. You have to sort of,
I mean, and it's not crazy to even try something like 1 to 100. I know of many growths where that works well and 1 to 20 works horribly. So it really is a matter of just trying some things.
Brian, can you show the other phase diagram you had that had a very steep melting curve?
Yeah, this one.
Yeah. So this one, for
There you
instance,
go.
if you
This
don't
is a
have
great illustration.
20 to 110 or more, and you're not above 600 degrees, you're not going to melt.
Yeah.
That's, this is kind of, for soft metals, is a very typical steep curve near the very rich phase of the lower melting point material. So that's
exactly right.
usually the thought process we have, that you need a lot, whether
Yeah.
it's 10, 20, or 100 or 200.
It's anyone's guess if you don't have the phase diagram.
Right.
Yeah.
Okay, so we better stop so that we can have a break.
Okay.
So Brian, thank you very much. We appreciate it.
Yeah, thank you. It was really fun. All right. I'm going to sign off. Have good coffee.
Okay, thank you, Ryan. Thanks for waking up so early, too.
Oh, sure. Anytime. Thanks, JP.